Why, hello. Today we're going to go on to section 15.5, which deals with the chain rule. And with the chain rule, let's recall that if z was a function of two variables, x and y, then what we learned last time was how we could compute what was called the total differential of z. And what dz gave you a measure of is approximately how much z changed when you changed x and you changed y. Now in this particular section, we're actually going to have z as a function of x and y, but then we're going to be told maybe that x is a function of two other variables, maybe, and it doesn't even have to be two other variables. It could be three other variables, four other variables, or maybe just a function of t. But x could be a function of, let's say, t and u, and y could be a function of, let's say, t and u. So if you plugged in x, what x equals in terms of t and u, and what y was equal to in terms of t and u, into this expression, in reality you could think of z as being some function of t and u. And then it makes sense, well, what's the partial of z with respect to t? What's the partial of z with respect to u? Okay, that's what's going on here. So, to do that, it's quite simple. Looking at the total differential here, if I wanted to compute what's the partial of z, let's say with respect to t, because x is a function of t and y is a function of t, what I tell my students to do, write out your total differential. Since z was a function of x and y, I'm going to write dz as the partial of f with respect to x dx plus the partial of f with respect to y dy. And all we're going to do is divide by dt on both sides, because I want to get the partial of z with respect to t. And right here, I just have dz. Well, if I divide through by dt on both sides, what I get is dz dt is equal to the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. And this is the chain rule for multivariable calculus. Notice we could have a function w that's a function of three variables, x, y, and z. And suppose I want to figure out how does w change with respect to t. Well, what I would do is I would take this total differential and say, oh, if I want to know dw dt, let's just divide through by dt on both sides. And you notice if you do that, what you get here is dw dt is equal to the partial of g with respect to x times dx dt plus the partial of g with respect to y times dy dt plus the partial of g with respect to z times dz dt. Now, you might wonder, when do you use the d and when do you use the partial? You use the d if x is just a function of time and nothing else, then we use the derivative like we had in Calc 1. Where if x is a function of maybe two variables, t and u, well then when you take your derivative it's called a partial, and then you use the italics kind of delta that we have. Let's do a couple of examples. Let's say that z is equal to x squared y plus 3xy to the fourth, and we're told that x is equal to sine of 2t and y is equal to cosine of t. All right, and they want me to figure out dz dt. Now notice they didn't write it as a partial, they wrote it as dz dt, because in reality, we could do this problem back, if you went back to your old Calc 1 days. You could say here, oh, Miss Strocko, well if z is equal to x squared y plus 3xy to the fourth, then z is equal to x is sine 2t. So where I see x, I can put in sine 2t, Miss Strocko. And since y is cosine t, I can put in y plus 3x, which is sine 2t, times y to the fourth, which is cosine t to the fourth. And as you can see, this is a Calc 1 problem. It's a bit hideous, but z is just a function of t. So when I take the derivative of z with respect to t, I don't use the partial notation. I use dz dt because I'm not holding anything constant when I'm taking my derivative. And you could differentiate this problem just like you did back in Calc 1. You'd look at this as a product, you know, and you'd look at this as a product, and you'd find the derivative of this plus the derivative of that. Now, we're not going to do that today. We're going to use Calc 3 techniques. So instead, I look at the problem, and what I say is, okay, what did they want me to find? They want me to find dz dt. That's what they want, dz dt. So I look and I say, okay, z is a function of x and y. So the total differential of z, dz, would be the partial of z with respect to x dx plus the partial of z with respect to y dy. And since they want dz dt, I'm just dividing through by dt on both sides. All right, so dz dt is equal to, and I look up here and I say, okay, what's the partial of z with respect to x? Well, looking at that, we're going to hold y constant, and we're going to take our derivative with respect to x. Well, that's going to give me, let's see, if y is constant, the derivative of this is going to be 2xy, right? Because y is a constant, and the partial of x squared is just 2x squared plus y to the fourth I look as a constant, so the derivative of 3x with respect to x is just 3. But now I have to multiply it times dx dt. So I look up here and I say, oh, let's see, x is equal to sine 2t, so dx dt would be, for my Calculus 1 days, derivative of sine is cosine times the derivative of what's inside, which is 2. So I'll have 2 cosine 2t here. Plus, we have to figure out the partial of z with respect to y. Well, coming back up here, since z is x squared y plus 3xy to the fourth, let's see, the partial of that with respect to y, this is like a constant times y, so its derivative is just x squared, plus taking the partial of 3xy to the fourth with respect to y, 3x is a constant, so I bring my 4 down, so I have 4 times 3x is 12x, y to the third, times, then we got to take dy dt. Well, if y is cosine t, dy dt is just minus sine t. Okay, now we're partially there, except they want us to find dz dt when t was 0. So I come back up here and I say, okay, let's see, when t is 0, notice x is sine of 2t, so that's sine of 0, which is 0. Y is cosine of t, so that's cosine of 0, which is 1. Okay, so when t is 0, if I plug in t equals 0 into here, I get, let's see, x is 0, so it's 2 times 0 times y is 1, plus 3 times y is 1 to the fourth, times 2 cosine of 0, plus x squared is 0, plus 12 times 0 times 1 to the third, times minus sine of 0. Okay, and simplifying that, let's see what we get here. We get this equals 2 times 0 times 1 is 0, 3 times 1 to the fourth is 3, times cosine of 0 is 1, so 2 times 1 is 2, plus blah, blah, blah. Sine of 0 is 0, so this is just going to be 3 times 2, which is 6. So dz dt evaluated at t equals 0 is 6. Okay? So if you notice, what we're doing in this section is if they want to know the partial of z with respect to t, just find out the total differential of dz and divide through by dt, and then you know what you're going to do. Okay, let's do a few more. Okay? This one, use the chain rule to find dz dt. Now notice, the reason they're saying dz dt instead of the partial of z with respect to t is, notice, z is a function of x and y. But x is totally a function of t, y is totally a function of t. So if I plug these two guys into here, I would have z totally a function of t. So it would be a Calc 1 problem, dz dt. But again, I look at this and I say, okay, no problem. Z is a function of x and y. So dz is equal to the partial of z with respect to x dx plus the partial of z with respect to y dy. And since they want dz dt, I'm going to divide through by dt. Okay? Now I prefer to write my z here as x squared plus y squared to the 1/2. Okay? So my dz dt is going to be, now let's see, what's the partial of z with respect to x? Well, I want to take the partial of that with respect to x, bring down my 1/2, leave x squared plus y squared alone, decrease the exponent by 1, 1/2 minus 1 is -1/2, times the derivative of what's inside, And the derivative of, now notice we're differentiating with respect to x. So the derivative of x squared plus y squared with respect to x is going to be 2x. Okay. We just did this one. Now we have to take dx dt. Well, let's see. dx dt is x is equal to e to the 2t. So if we want to differentiate x with respect to time, the derivative of e to the 2t is e to the 2t times the derivative of 2t with respect to t is 2. Plus, now we have to take the partial of z with respect to y. So z is equal to this, so if I take the partial of that with respect to y, again, I have something to a power, so I bring down my 1/2, leave this alone, decrease my power by 1, times, what's the partial of that with respect to y? 2y. Times, now we got to figure out dy dt. Well, y is equal to e to the minus 2t. And the derivative of e to the u is e to the u times the derivative of u, which is a negative 2. Now this is a bit horrendous, so let's see if we can clean it up a little bit. Let's see. Well, I'm looking here and I'm thinking 1/2 times 2, they cancel. Okay? And so this first thing, if you look at it, you have 2x e to the 2t times x squared plus y squared to the minus 1/2. The minus 1/2 says put me down bottom. So that would be x squared plus y squared to the 1/2. This second one, if you see, you have 1/2 times 2, they cancel. And we have a negative 2, y, e to the minus 2t, all over x squared plus y squared to the minus 1/2 is x squared plus y squared to the 1/2. Okay, and since these two fractions have the same denominator, we can put them together as one thing. So I'd have 2x e to the 2t minus 2y e to the 2t, e to the minus 2t, excuse me, all over square root of x squared plus y squared. Okay, and that's my final answer. Okay, shall we do another one? Now look at this one. Here, notice w is a function of x, y, and z, because we have w is equal to x times e to the y divided by z. Now I prefer to write that as w equals x times e to the y times z to the negative 1. That would be easier for me to take the derivative. Okay, because y over z is y times z to the negative 1. Now notice, we might just put a few things here. We have x is t squared, so dx dt would be 2t. We have y equals 1 minus t, so dy dt is a negative 1. And z is 1 plus 2t, so dz dt is 2. And that might come in handy in a few minutes. All right, so they want us to get, notice w is a function of x, y, and z, and they want us to get dw dt. So what I'm going to do first of all is say, well, what's dw? dw is equal to the partial of w with respect to x dx plus the partial of w with respect to y dy plus the partial of w with respect to z dz. And if they want dw dt, I divide through by dt on both sides. All right, so my dw dt is equal to, first, I have to have the partial of w with respect to x. So what do we have here? This is what w was. W was x times y over z, and I said I found it a little bit easier to write it as x times e to the y times z to the negative 1. Okay? All right, now let's see. We're differentiating that with respect to x. So this whole thing here is considered a constant. It's just one stinking constant times x. You have 5 times x. The derivative with respect to x is just 5. So it's just the constant e to the y z to the negative 1 times dx dt. Now a few minutes ago I figured out dx dt was 2t, so I can put that in. Plus, all right, now we have to get the partial of w with respect to y. So coming along back up here, what's the partial with respect to y here. This is a constant, so bring your constant along. The derivative of e to the u is e to the u times the derivative of u. Well, we're differentiating with respect to y. So what's the derivative of y z to the minus 1 with respect to y? Z to the minus 1, right? Because it's like y times a constant. Times, now I'm ready for dy dt. Well, we figured that out a few minutes ago. Dy dt was a negative 1. Then we have to go plus, now I'm doing the partial of w with respect to z. No problem. Let's see. This is again a constant. The derivative of e to the u is e to the u times the derivative of u. We're differentiating with respect to z. So this is a constant y. I don't like the way I wrote that. Let me write this way. Plus x times e to the y z to the negative 1. And now I got to figure out, I'm differentiating this with respect to z. And that's going to give me a constant, which is y. And the derivative of z to the minus 1 is minus z to the minus 2. You all with me? Because I'm taking the partial of this with respect to the partial of e to the y, z to the minus 1 with respect to z. So you're going to have e to the u, so that gives me e to the y, z to the negative 1. And the derivative of y, z to the minus 1 is the constant y. And the derivative of z to the minus 1 is going to be minus z to the minus 2. Times, now we got to do dz dt, and we did that a few minutes ago. dz dt was 2. Okay, now it probably would be nice to clean this up a little bit, so let's see what we have here. We have this is equal to 2t times e to the y times z to the minus 1 is y over z, plus, now let's see, this is going to be an x over z, and then times a negative 1, so I'll write that as a minus x over z times e to the y over z, plus, and let's see, this one's going to be now let's see, if I write it as a fraction, I have a negative, I have a 2xy in the numerator, and a z squared in the denominator, times e to the y over z, which if you ask me looks just fine, but if you wanted to, you could factor out e to the y over z and get 2t minus x over z minus 2xy over z squared would be your final answer. Okay. All right, and that's the one, where is the one that I just did? This is it right here. Okay, so we just finished this one right here, and that's what our final answer is. Okay, any questions? No? All right, let's look at this one. Now it gets complicated in this one, and let's look why. Because if you look, your z is given as a function of x and y. All right, they tell me that z is equal to e to the xy times tangent of y. That's what my z is. Now notice, x is a function of s and t, and y is a function of s and t. All right, if I write them out, which I will right here, we have, let's see, we have, okay, x is equal to s plus 2t, and y is equal to s over t, which I prefer to write as st to the negative 1 for differentiating. Okay, now, the one they want me to find out is the partial of z with respect to s. Now notice, z is a function of x and y, but since x is a function of s and y is a function of s, we can think of z as being a function of s. Now what I prefer to do, I mean, your book, you'll look, they do a thing with tables and that type of stuff. I prefer instead saying, no problem, z is a function of x and y. So dz is the partial of z with respect to x dx plus the partial of z with respect to y dy. And if they just happen to want the partial of z with respect to s, let's divide by partial of s on both sides. So our partial of z with respect to s is going to equal the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. Now these are partials here, not d's. because x is a function of two variables. So when you take your derivative, you hold the other constant. Okay, so let's do this one now. Let's see here. First of all, the partial of z with respect to s is, now first of all, I'm going to figure out this part. The partial of z with respect to x. So I look here and I say, okay, I have to differentiate this with respect to x. So we consider y a constant. So tan y is just a constant. So we have tan y times whatever the derivative of e to the xy is. So that's going to be, the derivative of e to the xy is e to the xy times the derivative of xy with respect to x would be y, times my constant tangent of y, times, now we got to get the partial of x with respect to s. Well, looking at this right here, I have x equals s plus 2t. So I want to get this right here. Well, if x is equal to s plus 2t, the partial of x with respect to s is 1. Plus, now we got to do the partial of z with respect to y. So I go back here and I say, okay, z is equal to e to the xy times tangent y. I have to differentiate that with respect to y. Unfortunately, I have a product here, don't I? I have to go first times derivative of second plus second times derivative of first. So it gets a little messy, but it's not impossible. So to take the derivative of that, it's first times. Now the derivative of tangent y with respect to y is secant squared y. Plus the second, tan y, times the derivative of the first. Derivative of e to the xy is e to the u, times the derivative of u, which is our xy, with respect to y is x. Times, now we got to figure out what's the partial of y with respect to s. Well, a few minutes ago, we had y equal to st to the minus 1. So the partial of y with respect to s, consider t to the minus 1 a constant. Well, a constant times s is just going to be the constant. Okay, and if I want to clean this up just a little bit, okay, let's see what we have here. We would have, let's see, usually you like to put the constant in front, so we'll write this as y e to the xy tangent of y times 1 plus, now let's see, does everybody realize t to the minus 1 you could write as 1 over t. So if you went this times this, you would end up with e to the xy over t times secant squared y plus, and when you go this times this, it would be e to the xy times x over t times tangent y. Okay, if I multiplied it out. If you wanted to, you could see that this has e to the xy, this has e to the xy, this has e to the xy. So if you wanted to, you could factor out an e to the xy and get e to the xy times y tangent y plus secant squared y over t plus x tangent y over t. Could be your final answer. There's multiple ways that you could write out this final answer. Okay, and this is fine. Okay, not hard. Okay, let's do another one. Again, in this one, oh, we just did this one. Good, good, good. Oh, no. Now, exact same problem, but they want the partial of z with respect to t. So you go, oh, Miss Strocko, all right. Notice, z is a function of x and y. So what I would do, I would say, okay, dz is the partial of z with respect to x dx plus partial of z with respect to y dy. So if you want the partial with respect to t, just divide by partial with respect to t on both sides. Now we just did some of this, so let me just copy what I had here. When I went partial of z with respect to x, I have all this, and partial of z with respect to y, I have all this. Do you mind if I just copy them down that we just did? We just did those. So I have, let's see here, partial of z with respect to t is equal to, for partial of z with respect to x, just a few minutes ago we got e to the xy, y tangent y, times, I'll figure out the x dt in a minute. And for partial of z with respect to y, I got this mammoth e to the xy secant squared y plus tangent y e to the xy times x. I just don't feel like doing it all over again. All right? You with me? Because this was the partial of z with respect to x, and this huge thing right here that I just copied was the partial of z with respect to y, which we did a few minutes ago. Now the only difference is we have here x is equal to s plus 2t. In this instance, what we have left to do is figure out the partial of x with respect to t. Well, if x is equal to s plus 2t, what is the partial of x with respect to t? 2. And what is, if y is equal to st to the negative 1, what's the partial of y with respect to t? Well, s is a constant, so you bring it along, and the derivative of t to the minus 1 is going to be bring down your minus, leave this alone, decrease your power by 1, so you could write that as minus s over t squared if you wanted to. So for partial of x with respect to t, I just put in a 2, and for partial of y with respect to t, I'm going to put in minus s over t squared. And the rest is simplifying using a little bit of algebra. If I write this out, I'd get 2y e to the xy tangent of y. And then I go this times this, I get minus s e to the xy secant squared y over t squared. And if you take this times this, let's see, you'd get a minus s tangent of y e to the xy x all over t squared. And to tell you the truth, I think that's fine. You know, you can go nuts in terms of simplifying, factoring out whatever you want to do. Okay? So the point is, the differential just tells you what to do. All right? This one, now we notice r is a function, u is a function of r, and r is a function of x, y, and t. You see that? U is a function of r and s. R is a function of x, y, and t, and s is a function of x, y, and t. So if I plug these into here, we could think of u as being a function of x, y, and t. So it makes sense to talk about what's the partial of u with respect to x, u with respect to y, and u with respect to t. I'm not going to do all of them, all right, because otherwise I'll put you guys to sleep. But thinking this through now, this one, it says use the chain rule to find the partial derivative when x is blah, blah, blah. We don't plug these in until the bitter end, okay? So first of all, to keep your head straight, you just say, okay, u is a function of r and s. So the du would be the partial of u with respect to r, dr, plus the partial of u with respect to s, ds. Now, if they want to have the partial of u with respect to t, all you have to do is divide by partial with respect to t on both sides. That's all you have to do. Now, I have to figure out partial of u with respect to r, partial of r with respect to t, partial of u with respect to s, partial of s with respect to t. Let's do these on the side. If u is r squared plus s squared to the 1/2, what is the partial of u with respect to r? Well, bring down your 1/2, leave this alone, decrease your power by 1 times the derivative of what's inside. Well, we're differentiating with respect to r, so the derivative of r squared with respect to r is 2r, and derivative of s squared is going to be 0. So, as you can see, the 2's cancel here, and I will have r over square root of r squared plus s squared for my partial of u with respect to r. Partial of u with respect to r, we just figured out, was r over square root of r squared plus s squared. Now, we'll do dr dt in a second. I'm just going to leave that as a blank. Plus, let's do partial of u with respect to s. Well, here, let's see what we have here. We have u is equal to r squared plus s squared. So if I wanted to figure out partial of u with respect to s, you would bring down your 1/2, leave this alone, decrease your power by 1 times differentiating r squared with respect to s is Zippo. Derivative of s squared is 2s. The 2's cancel. And you get s over square root of r squared plus s squared, which I will put right here. Now, what's left is we've got to figure out the partial of r with respect to t and the partial of s with respect to t. Well, let's see. We have here r is equal to y plus x cosine t. And we've got to get the partial of r with respect to t. Now, notice in this case, x and y are held constant. So if you differentiate y, you're going to get a big 0. This is a constant x times, and derivative of cosine t is minus sine t. So it looks like we would get a minus x sine t. So right here, minus x sine t. And lastly, we've got to figure out what's the partial of s with respect to t. Well, again, s is equal to x plus y sine t. So the partial of s with respect to t, that would be 0. This is a constant. Derivative of sine t is cosine t. So we just get y cosine t. So this is what our partial of u with respect to t looks like. Blah, 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 blah. Now we just have to play plug in. Now, to play plug in, what are they saying? Let's see. Notice my answer has r's, s's, x's, t's, and y's in it. All right, and they're telling me x is 1, x is 1, y is 2, t is 0. Now notice r is y plus x cosine t. So y is 2, x is 1, cosine of 0 is 1, so that's 2 plus 1 is 3. And lastly, let's see, s is x plus y sine t, plugging in 1 in for x, 2 in for y, and 0 in for t. Sine of 0 is 0, so this is 1 plus 0, which is 1. Okay, so now I'm ready to plug these in. So let's see. I have r over square root of r plus s squared. We figured out that r was 3. R is 3, so 3 squared is 9. S is 1. Times minus x, x was 1, and t was 0. Plus s over r squared. S was, we figured out, 1. And I just figured out r squared plus s squared was 10, so it's square root of 10, times y is 2, and t is 0. Now the good news is sine of 0 is 0, and 0 times a negative 1 is 0, and 0 times anything is 0. So this is 0, plus 1 over root 10 times cosine of 0 is 1, so we get 2 over root 10. So it's a bit tedious, but it's not difficult. Okay. All right, I think we've done enough of those. So let me show you something else. You might remember back in Calculus 1, we did implicit differentiation. And in fact, in I think the section on partial derivatives, we did a little section on implicit differentiation. And a lot of times students struggle with implicit differentiation. It's something that they had trouble with in Calc 1, and you might have had problems with in that one little section in Calc 2. Notice, back in your Calc 1, let's just review. The way we did it back in Calc 1 is if you had x squared plus y squared is equal to 0, and you wanted to figure out dy dx, you differentiated both sides with respect to x. So you differentiated x squared with respect to x. You differentiated y squared with respect to x. You might remember doing that. And the way you did it back in your Calc 1 days, the derivative of x squared was 2x. The derivative of y squared was 2y times dy dx. And then you would solve for dy dx. And if I want to solve for dy dx, I divide by 2y on both sides. So I get dy dx is minus x over y. And that's all well and good. You know, that's the one way to do it. We can do it using multivariable calculus. So let me show you. And I prefer it this way. In fact, I think it's It's an easier way to keep your head straight in what you're doing. Let me show you. What I'm going to do is I'm going to look at this x squared plus y squared equals 0. I'm going to look at this as I had x squared plus y squared equals 0. I'm looking at it as some function f of xy is equal to 0, where f of xy is x squared plus y squared. And we're saying that f of xy is equal to the constant 0. Okay, now don't frantically sit down and copy, just sit and follow for a minute, all right? Now watch what happens here. If big F, is a function of x and y, and it is equal to 0, then its total differential is equal to 0. And you say, why is that the case? Because f is never changing. F is always 0. So if you ever say to me, how much does f change? It's 0, because it's not changing. But we know from what we did the other day that since f was a function of x and y, its total differential was equal to the partial of f with respect to x dx plus the partial of f with respect to y dy. So this is equal to 0. So I can take this expression and I can solve for dy dx. Now how am I going to do that? Well, first I'm going to throw this to the other side. Okay, now if I want dy dx, I'm going to divide by dx on both sides, and I'm going to divide by partial of f with respect to y on both sides. And look what I get here. I could, and I'll do that problem in a second, dy dx is just equal to minus the partial of f with respect to x over the partial of f with respect to y. Now I'll be honest with you, a lot of times I forget these formulas, and so you know what I do? I derive it, because I go, what's the total differential? Let's solve for dy dx, and I can get it. Students that like to memorize, notice you wrote it as f of xy is equal to 0. You have to have f big F being equal to 0, or at least being equal to a constant. Notice you're saying, I'm assuming y is a function of x, so dy dx is, notice, it's sort of flip-flopped. Since x is on the bottom here, the partial of f with respect to x is on top. And since y is on the top, on the bottom is the partial of f with respect to y. So back when you had me for Calculus 1, and you had to find the implicit derivative, you know, doing this, and I taught you this way. What I always did, I would say, oh, we have x squared plus y squared is equal to 0. I said, oh, big F is equal to x squared plus y squared. So if they want to know dy dx, it's minus the partial of f with respect to x over the partial with respect to y. And I go, okay, that's minus, let's see, partial of that with respect to x is 2x, partial of that with respect to y is 2y. Oh yeah, I see the x's cancel. And that's my final answer. Much quicker, because you think about how those implicits got. You had to do all that factoring and everything. It got pretty bloody. This is nice and simple. So, and what I have here is what I just wrote out. It's taking this and solving for dy dx, and that's what I did right here. So, what if I want to do this? I have, and this would be a messy, 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 hideous implicit derivative to give to you guys in Calc 1. But I'm assuming that y is a function of x, and I want to figure out what dy dx is. First of all, I have to put this in the form of f of xy is equal to 0. So I'm going to let f of xy be y to the 5th plus x squared y cubed minus 1 minus y e to the x squared. And that indeed does equal 0, because I subtracted everything on both sides. So since I have f of xy is equal to 0, if I want to get dy dx, that lovely formula that we derived said it equals minus the partial of f with respect to x over the partial of f with respect to y. And you can factor that minus and put it out front if you want. So if I look at this and I say, what's the derivative of that with respect to x? Well, we're holding y constant, so that's a 0. Derivative of that's going to be 2xy cubed. Derivative of 1 is 0, and derivative of minus y e to the x squared is going to be minus y. Derivative of e to the x squared is e to the x squared times 2x. If I want to take on the bottom partial with respect to y, I'm differentiating the same thing with respect to y, so I get 5y to the 4th. Differentiate this with respect to y would be x squared times 3y squared, so I'll write it as 3x squared y squared. Derivative of that is a constant, and derivative of minus y e to the x squared, well, e to the x squared is like a constant, so a constant times y, if you're differentiating with respect to y, is just going to be e to the x squared. And I'm finished. This is my final answer, which was a lot easier to do than what you had before. Okay? All right, we doing okay? Now, we can kick this up a notch. Look at this, and I'll be honest with you, if I have this, I can't remember it, I usually always derive it, but notice, suppose you have f of x, y, z equals 0. Right, so I have an equation in terms of x, y's, and z's, and I'm going to assume that I can write z as a function of x and y. So I would like to figure out what's the partial of z with respect to x, and what's the partial of z with respect to y. All right, now, we are going to assume that z is a function of x and y. So suppose we want to get the partial of z with respect to x. Now, if you take the partial of z with respect to x, what do you hold constant? Aha! Hold y constant. Okay, hold y constant. So what I do is this. I say, okay, if f is a function of x, y, and z, I know from last night's homework that df is partial of f with respect to x dx plus partial of f with respect to y dy plus partial of f with respect to z dz, and that is equal to 0 because f is equal to 0, so f is not a change-in. Now, if I wanted to figure out the partial of z with respect to x, since y is being held constant, what does dy equal? 0, because y is not a change-in. dy, which is delta y, is 0. So this is a big old 0. So with this lovely little equation here, people, if they wanted to know the partial of z with respect to x, well, let's get dz and dx over each other. So I'll have partial of f with respect to z dz is equal to minus partial of f with respect to x dx. Now, since I want dz dx, I'm going to divide by dx on both sides. So they're gone. And I'll divide by partial of f with respect to z on both sides. This should be a capital F, I apologize. And I just divide it by that. And I got that. And notice I have, if f is a function of x, y, and z, if I want to know what the partial of z with respect to x is, it's just like that other formula I have. Notice it's minus the partial of f with respect to x over the partial of f with respect to z. Now notice, if I had here df equals partial of f with respect to x dx plus partial of f with respect to y dy plus partial of f with respect to z dz equals 0, because why? Because f was equal to 0. If we're assuming z is a function of x and y, and we wanted to get the partial of z with respect to y, well, when you take the partial of z with respect to y, what's held constant? X. So if x is being held constant, what is dx equal to? 0. So this part drops out. And so if I want to get partial of z with respect to y, I want to get the dz and the dy over each other. So I'd have fz dz is equal to minus fy dy. I'm going to divide by dy on both sides. That's gone. And so I get partial of z with respect to y is minus fy over fz. And notice the beauty of this. It's minus the part, see, this is on the bottom, so partial of f with respect to y is on top. And this is on top, so these on bottom, partial of f with respect to z. Now, if you forget the formula, it's really easy to derive it. But now here in your lecture notes, I have the derivation all written out for you, but I prefer to write it myself, derivation all over again. But in summary, If you have f of xyz equals 0, and we're assuming z is a function of xy, then the partial of z with respect to x equals minus the partial of f with respect to x over the partial with respect to z, and the partial of z with respect to y is equal to minus the partial of f with respect to y over the partial with respect to z. I think it'd be a fair question on a test to ask you to derive it, because I think the derivation's not all that hard. But here, I have xyz equals sine of 2x plus 3y plus 5z, and I want you to find the partial of z with respect to y. We are assuming that z is a function of x and y. First of all, what we have to do is we have to write f of x, y, z as a function that equals a constant. So I'm just going to subtract sine of 2x plus 3y plus 5z on both sides, and I can see that f of x, y, z equals 0. So what we just derived a few minutes ago, they want us to get the partial of z with respect to y. If you notice, a few minutes ago, we derived that this is equal to minus fy over fz. So looking at this function right here, this will equal minus, and I go, what's the partial of this with respect to y? Oh, well, the partial of xyz with respect to y is just xz. And I have minus, derivative of sine is cosine, times the derivative inside. I'm differentiating with respect to y, so it'd be 3. Over, now we want to differentiate with respect to z. Well, if I differentiate xyz with respect to z, I get xy minus derivative of sine is cosine times the derivative of what's inside. We're differentiating what's inside with respect to z. I get a 5, and there's my final answer. Not hard to do, but you do need to practice. Okay? All right, now let's do an application with this. All right. The radius of a right circular cone is increasing at a rate of 1.8 inches per second, while its height is decreasing at a rate of 2.5 inches per second. At what rate is the volume of the cone changing when the radius is 120 inches and the height is 140 inches? Now let's first of all write down what we know here. The radius of a right circular cone is increasing at a rate of 1.8 inches per second. What are they giving you there? You're going back to your Calculus 1 days. They're giving you, what are they giving you there? The radius is increasing. They're giving you dr dt. And it's increasing, maybe I put it in red because that means it's a plus, 1.8 inches per second. Then they say the height is decreasing at a rate of 2.5. So dh dt, since it's decreasing, it's a negative 2.5 inches per second. They want to know the rate at which the volume is changing, so they want to find dv dt when the radius is 120 and the height is 140. This is what they want us to find out. dv dt, how is v changing with respect to time? Well, does anybody know what's the formula for the volume of a cone? Look in the front. I should mention this. Notice, I think everybody in Calc 3 should know this. If you have a cylinder, the volume of a cylinder is the area of the base times the height. Okay? Now the way I remember the volume of a cone, and I think you guys are getting to the point where, we should have certain things at our fingertips. If I take this cylinder and I pick this point, this will sort of help you memorize it. There's my cone. All right? Do you see, sort of pictorially, that the cone takes up just 1/3 of the cylinder? So the volume of the cone is just 1/3 pi r squared h. Okay? All right. So now, guys, you just told me the volume of a cone is 1/3 pi r squared h. Notice, my volume is a function of r and h. They want to have dv dt. Don't worry about dv dt right now. Let's just worry about dv. Right now, volume is a function of r and h. So dv would be the partial of v with respect to r dr plus the partial of v with respect to h dh. Okay, you all with me? By the way, what is the partial of v with respect to r? Using this. Bring down your 2, so it would be 2/3 pi rh, right? Times dr. I don't know dr right now. What would be the partial of v with respect to h? Just 1/3 pi r squared, right? There I just wrote out my total differential. But what do they want? They want dv dt. So what do you think I'm going to do? Divide by dt. Okay. And they want me to figure out dv dt when r is 120, h is 140, and these rates are what's happening. So now it's just plug in time. So let's see. I have 2/3 pi. My r is 120. My h is 140. And dr dt is plus 1.8 plus 1/3 pi. My r is 120. And there's no h to plug in, but dh dt is a negative 2.5. Now, if you leave pi in the answer, treat pi like an x, and multiply this out, plus multiply this out with your coefficients, you'll end up with 8160 pi. I don't feel like turning on the calculator, but you just simplify that, you get that. By the way, what are my units going to be? It's dv dt, how my volume is changing with respect to time. So if I'm measuring my radius in inches, what's my volume measured in? Cubic inches, and my time was seconds. Just the old plug and chug. One more, and then I promise we will call it quits. Let's look at this one. The length, width, and height of a box change with time. At a certain instant, the dimensions are length is 1, and width equals height equals 2. And the unit they're using is meters. And L and W are increasing at a rate of 2 meters per second. What are they giving us there? They're telling us how length and width are changing with respect to time. So they're telling me dl dt and dw dt are plus 2 meters per second, while h is decreasing at a rate of 3 meters per second, so that's going to be a negative 3 meters per second. At that instant, when the height are this, and the dl dt's and dh dt's are this, at that instant, find the rate at which the volume is changing. So what are they asking me to find? They want me to get dv dt. That's what they want. So I go, oh, I've got myself a box. Right? It has a length, it has a width, it has a height. Last time I looked, volume was length times width times height. Now they want dv dt, but I'm not going to worry about that. I'm first going to worry about just getting dv, because notice my volume right now is written as a function of 3 variables. So dv is equal to the partial of v with respect to L dl plus the partial of v with respect to w dw plus the partial of v with respect to h dh. Now, if you want to, you can multiply through by dt right now if you want. If you want to divide through by dt, be my guest. But do you see where the dt's are going? They're going over the little differentials for L, W, and H. So dv dt is, now what's the partial of v with respect to L using this formula? WH. What's the partial of v with respect to W? W is able to change. This is just like L and H is a constant times W. It's just going to be LH. And what's the partial of V with respect to H? It's just LW. And now it's time for us to do some plugging in. Let me turn this, let's fold this over so we can see what I just wrote. And slide this up so we can see what we're plugging in. So let's see. Plugging this in, I get W times H. So that's 2 times dl dt is 2. Plus L times H. L is 1, H is 2, dw dt is 2. Plus L is 1, W is 2, and dh dt is a negative 3. So it looks like I have an 8 plus 4 minus 6. Well, 8 and 4 is 12, minus 6 is 6. It's important to give the units, though. It's how volume is changing with respect to time. We measured our distance in meters, so volume would be cubic meters per second. Okay? I think we did plenty for today. So what I want you people to do is read pages 967 to 973, and then you really should do exercises 1 through 11, the odds, 21 to 33, the odds, and then number 39. Okay? It's been delightful. See you next time. Bye-bye.